Welcome to this explainer. You know, set theory often sounds incredibly intimidating, but today we're turning it into something completely intuitive. If you've ever felt overwhelmed by mathematical jargon, don't worry, I've got you covered. As I was digging through this material, it hit me. We shouldn't think of set theory as some scary, abstract math. It's actually the ultimate mathematical filing system. Literally, it's the science of organizing the world into neat, manageable categories. By the time we wrap up, you're going to see just how simple, powerful, and honestly how elegant this whole system really is. Let's get into it.
So, here is our agenda for today. First, we'll hit the basics of sets. Then, 3 ways to write sets. Third, the golden rules of sets. Next up is categorizing types of sets. And finally, how sets interact. And hey, for those of you studying, I'll be dropping some crucial CDACC exam tips along the way, so stick around for those.
Section 1. The basics of sets. Okay, let's dive into this.
We hear the word thrown around a lot in math, logic, and even computer science. But if we strip away all the complex formulas and the jargon, what exactly is a set at its absolute core?
Well, a set is simply a collection of objects that belong together. Think of it just like a basket. Everything you toss inside that basket belongs to that specific set, and we call those objects elements or members. If an object is inside our basket, we use a special little symbol. It looks kind of like a curved E to say it belongs to the set. And if it's not in the basket, we just cross that symbol out to say it does not belong. But, and this is a massive catch, a set absolutely must be well defined. What does that mean? It means anyone, anywhere should be able to look at an object and know with 100% certainty if it goes in the basket or not. For example, the months with 31 days. Perfectly well defined. We all agree on what those are. But what about a set of beautiful cars? Yeah, that doesn't work. Beauty is totally subjective, right? Since there's no clear universal rule for what makes a car beautiful, it just cannot be a proper set.
Section 2. 3 ways to write sets. Now that we know what sets are, we need to learn how to actually speak this language.
There are 3 main ways we can describe the exact same basket of numbers. First up is the roster, or tabular form. This one's the most straightforward. You literally just list every single element inside curly brackets. Boom, 2, 4, 6, 8. Second is the set builder form. Instead of listing everything, which, let's be real, gets exhausting if you have 1,000 numbers, you just state the rule. You use a vertical line in there and you just read that as such that. So it translates to A is the set of all x such that x is an even number less than 10. Finally, we have the statement form. No math symbols here, just plain ordinary English. The absolute crucial point to remember is that all 3 of these methods are describing the exact same elements. You're simply choosing your level of mathematical notation.
Section 3. The golden rules of sets. Before we start building complex ecosystems, we have to lay down the absolute laws of the land.
Rule number 1. No duplicates. In set theory, an element can only appear once. Let's say we have a basket with a bunch of repeating 2s and 3s. Well, repeating an element doesn't magically create a brand new one. The basket either contains the number 2 or it doesn't. Simple as that. Therefore, a heavily padded set with extra 2s and 3s is exactly 100% identical to a simple set of 1, 2, 3. Duplicates are completely ignored.
Rule number 2. Order does not matter. Now, this is where a lot of people trip up. When you use curly brackets, the set of 1, 2, 3 is mathematically identical to the set of 3, 2, 1. Only the contents matter, not how they're arranged in the basket. But you have to contrast this with a sequence, which uses parentheses instead. In a sequence, position is everything. A sequence of 1, 2, 3 is absolutely not the same as 3, 2, 1. So remember, curly brackets mean it's a set. And in a set, you can shuffle the items around all day long and it remains exactly the same set.
Section 4. Categorizing types of sets. This is one of the easiest places to score points if you just know the tiny differences between definitions.
First, we divide sets by how big they are. A finite set has a fixed limit. You can count all the elements and eventually stop. And here's a quick pro tip. Even if a set has 1,000,000 elements, it's still finite because it does eventually end. An infinite set, on the other hand, well, it goes on forever. You'll usually see 3 little dots at the end of the curly brackets. Those dots mean the pattern continues indefinitely. No matter how long you count, you will never, ever finish.
Next up is the big boss, the universal set, represented by a capital U. The universal set contains absolutely everything being discussed in your current problem. I really love this analogy. Think of the universal set as an entire country. Every other set we talk about is just a smaller county inside that country. Every single element in every other set is pulled directly from that universal set. It acts as the absolute boundary of our mathematical universe for that specific problem.
At the complete opposite end of the spectrum, we have the empty set or null set. This is a basket with absolutely nothing in it. You'll see it represented by a 0 with a slash through it or just empty curly brackets. But don't let its emptiness fool you. It is incredibly important because it's mathematically considered a subset of every single set in existence. Then we have the singleton, or unit set. This one contains exactly one element. Notice how a number like 5 can be placed inside curly brackets? The number 5 by itself is just a number, but those brackets are what magically turn it into a singleton set.
Section 5. How sets interact. Okay, let's shift focus to see how these building blocks interact with each other in the wild. The most common interaction you'll see is the subset. Imagine a large school. A classroom is a subset of that school because everything inside the classroom is also inside the school, right? But we have to distinguish between a regular subset and a proper subset. A standard subset, which has a little line under the symbol, means inside or equal. Every element of the first set is in the second set, but they could actually be the exact same set. In fact, a highly tested rule to remember is that a set is always a subset of itself. Now, a proper subset lacks that bottom line. It means inside only. It has to be strictly smaller. For the first set to be a proper subset of the second, the larger set must contain everything the smaller one has, plus at least one extra element. It has to be bigger.
Now, what's really interesting here is a massive trap that catches students all the time. It's a difference between equal and equivalent sets. Equal sets are exactly what they sound like. They have the exact same elements. 1, 2, 3 is perfectly equal to 3, 2, 1. Equivalent sets, however, only care about the size of the basket, not what's inside it. So a set of 1, 2, 3 has 3 elements. A set of dog, cat, goat also has 3 elements. Therefore, they are perfectly equivalent, even though their actual contents have absolutely nothing in common.
So, the absolutely crucial takeaway here is this. Let this sink in. Equal sets are always equivalent because they have the exact same items, meaning they naturally have the same number of items. But equivalent sets aren't always equal. Just because 2 baskets both hold 3 items doesn't mean they're holding the same 3 items. Grasping that one sentence is your key to conquering comparison questions.
When we compare sets side by side, we can also see if they share anything. Overlapping sets share at least one element, so if both sets contain the number 3, they overlap. If you picture a Venn diagram, these are 2 circles that cross over each other in the middle. Disjoint sets, on the other hand, have absolutely 0 common elements. A set of 1 and 2 has nothing to do with a set of 4 and 5. In a Venn diagram, these are 2 circles sitting completely separate from one another, never touching.
Before we make our final push, let's quickly recap the ecosystem using this summary. We've got the universal set containing everything and the empty set containing nothing. We have subsets that sit inside other sets and proper subsets which are strictly smaller. And we have overlapping sets that share elements alongside disjoint sets that are completely isolated. Seeing it all laid out like this really highlights just how logical the whole ecosystem of set theory truly is.
And as promised, for our focused learners preparing for their CDACC exams, here is your VIP checklist. If you want to ace this section, make sure you can seamlessly translate between statement, roster, and set builder forms. Be able to instantly spot the difference between finite and infinite sets. Know exactly when to use the belongs to and does not belong to symbols. And above all, tattoo these 2 rules in your mind. Duplicates are entirely ignored, and the order of elements absolutely does not matter inside those curly brackets.
We have covered a lot of ground today, organizing the mathematical world into perfectly well-defined baskets. But I want to leave you with a slightly philosophical thought based on everything we've just learned. If we zoom all the way out and the literal universe is our ultimate universal set, containing everything in existence, what exactly is its empty set? Think about that for a while. Thanks so much for joining me on this explainer, and keep that curiosity alive.